When we think about 6G, our minds jump to these incredible futuristic ideas, right? Holographic calls, digital worlds, everything connected all the time. But that future, it's being built on a totally new foundation called Open RAN. And the path to get there, well, it's a bit of a labyrinth. So today we're going to try and find our way through it.
And that, right there, is the key. This isn't just about making your phone a little bit faster. We are talking about fundamentally ripping up the blueprints and redesigning wireless networks from the ground up. And the idea, at the very heart of that massive shift, is Open RAN.
You know, for decades, networks were pretty simple in a way. You bought one big, sealed black box from a single company. That was it. O-RAN wants to totally smash that model. The dream is to build a network like a set of Lego blocks, where you can snap together software from one company with hardware from another, all managed by smart AI. The promise? More competition, way more innovation, and a much, much smarter network.
Okay, but here's the catch. Between that amazing vision and a 6G network that actually, works, there's this maze of really tough problems. And it's not just one single issue, it's a whole stack of them at every single layer of the system.
So, here's our game plan. We're going to peel back these layers, one by one. We'll start right down at the bottom with the physical hardware, then move up to the software in the cloud, then we'll tackle the AI brain, and finally, see what happens when all these smart pieces try to work together. This is our map.
All right, first stop, the very foundation, the physical hardware. Before you can build a fancy, intelligent network, you've got to get the basic plumbing right. And believe it or not, this is turning out to be one of the fiercest battlegrounds.
So, in this new O-RAN world, the traditional cell tower, it gets split into these three main parts. You've got the radio unit, or RU. That's the part that actually talks to your phone. Then you have the DU and the CU, the distributed and centralized units, which are basically the brains doing all the processing. This split is the whole key to making it open.
And that, right there, is the multi-billion-dollar question. I mean, for all these different Lego blocks from different companies to work together, they need a perfectly standardized way to communicate. And that is where the fight begins.
And this isn't just some technical debate, it's a political one. That critical link between the radio and the processor is called the front haul. And there is a massive industry-wide battle over what the standard for it should be. You've got the O-RAN Alliance pushing their version, while some of the big established players are pushing back, worried about performance and security. If we don't get a single global standard, we risk creating different, incompatible flavors of 6G, which is the exact problem O-RAN was supposed to fix in the first place.
Okay, let's move up the stack. So let's assume for a minute we solve all the physical connection problems. The next layer is software. This is the virtualization challenge. Can we take these super-sensitive radio functions and run them on generic off-the-shelf cloud servers? And this is where things get intense. See, unlike a website or a normal app, radio networks are brutally, unforgivingly sensitive to timing. We are talking about microseconds. A tiny delay isn't a small glitch, it's a catastrophe that can knock the whole connection offline. So, right away, this creates two huge problems. First, there's the physics of it. Just trying to guarantee that microsecond performance on a standard server is an unbelievable engineering challenge. But then, there's the accountability maze. In the old days, with a single black box, you knew exactly who to call when things broke. But now, in a multi-vendor world, if software from company A running on hardware from company B crashes the network, whose fault is it? Who do you call? It's a legal and operational nightmare. In fact, this accountability problem is so thorny, so complex, that you won't believe what they're looking at to solve it. Researchers are seriously exploring things like blockchain and even large language models, just to create a secure, unchangeable log of what every single component did and when. That's how hard this is. So now we arrive at the brain of the network, the intelligence layer. This is where AI is supposed to be optimizing everything, making the network faster and more efficient in real time. But this brings up a challenge that's less about engineering and a little more about philosophy.
The issue, in a nutshell, is this. A lot of the most powerful AI models are, for all intents and purposes, a black box. We can see the data that goes in and we can see the decision that comes out, but we often have no idea why the AI made that specific choice. And this quote just nails it. We are essentially handing over the keys to a self-driving network that has no dashboard, no steering wheel, and no windows. If an AI suddenly decides to drop service for an entire hospital or reroute traffic for a fleet of autonomous cars, the human operators have to know why. Without that, how can we possibly trust it? We'd be completely flying blind.
So what's the answer? Well, there's this whole field called explainable AI, or XAI for short. And let me be clear, this isn't some optional, nice-to-have feature. For 6G, it is an absolute, non-negotiable requirement. We have to build systems that can explain their own logic, that make the AI's decisions transparent and auditable. We have to bake trust right into the network's core.
All right, we've made it to our final layer, the control plane. This is where all those cool, intelligent applications are supposed to live. But here, we find a final, kind of ironic twist. Sometimes, being too smart can actually make the network dumb.
Let me give you a really simple example. Let's say you have two different AI apps running on the network. One app's only goal is to save energy, so it's trying to power down a radio. But at the exact same time, another app sees a huge crowd of people, and its goal is to boost capacity, so it tries to power up that very same radio. They are literally telling the hardware to do opposite things. The result is pure chaos. The radio's power level just bounces back and forth, creating all this instability. In the end, the network can actually perform worse than if you just turn the smart apps off completely. It turns out, without careful coordination, intelligence can seriously backfire.
So, the huge question for 6G becomes this. How do you build an air traffic control system for the network's brain? We're going to need some kind of master framework that can understand what all these different AI apps are trying to do, and then harmonize our decisions before they start fighting with each other. So, there you have it, our journey through the layered labyrinth of 6G. We started with the pure politics of getting hardware to agree on a standard. Then, we climbed into the hard physics of making cloud software work in microseconds. We wrestled with the philosophy of whether we can trust a black box AI, and we finished with the simple logic of stopping smart apps from stepping on each other's toes.
But here's the thing. These hurdles, they shouldn't be seen as deal breakers. They are the defining engineering challenges that are going to shape the next decade of our connected world. Solving these problems is what will finally unlock that incredible 6G future we're all dreaming about. And that really leaves us with one big final thought. As we build this next generation of our digital world, maybe the toughest challenges aren't just about writing better code or designing faster chips. Maybe the real work is solving these fundamental problems of politics, physics, and even philosophy. Thanks for joining me.